Hello everyone, this is Jordi Pont-Tuset from Google Research, and I'll present our work Connecting Vision and Language with Localized Narratives. Language is a very important part of human intelligence. It is an abstraction of real-world concepts, many of them learned from visual inputs. In order for machines to be able to learn this matching between words and visual concepts, image captioning was one of the tasks that were proposed, where the content of an image is described with a sentence. The link between vision and language, in this case, is only at the level of full image to one sentence. To improve this linking, people took some specific words in the captions and drew the image regions they referred to. This process is called visual grounding. For instance, in this case, the dog or the van are grounded on specific regions of the image. But the links are still very sparse. Only a few words are grounded, and it's expensive to annotate. Annotators need to go back to the image, read all captions, draw the boxes, etc. In localized narratives, we propose an annotation protocol that enables much tighter grounding of a caption into an image. The instructions we gave to the annotators are very simple. Use the mouse to point at the object in the scene. Simultaneously, use your voice to describe what you are pointing at. Speaking and pointing is very natural to humans and can be done in parallel effortlessly. The synchronicity between mouse and voice allows us to localize words in the description by knowing where the mouse was located when the annotator pronounced each word. We encourage the annotators to focus on concrete objects, say the relationship between objects, mention adjectives, and indicate the extent of an object by moving their mouse over it. Let's watch a localized narrative obtained with this protocol. The red circle represents the annotator mouse. The text on the right is the full image caption they provided, and the red box highlights the word that the annotator is speaking at a certain moment in time.
In the front portion of the picture, we can see a dried grass area with a dried twigs. There is a woman standing wearing a light blue jeans and ash color long sleeve length t-shirt. This woman is holding a black jacket in her hand, and on the other hand she is holding a balloon which is peach in color. On the top of the picture we can see a clear blue sky with clouds.
Each word is therefore associated with a mouse trace grounding it on the image. This includes concrete nouns such as jacket, clouds, but also relationships such as holding. So how did we derive the localized narrative you just saw from the annotator's input? The raw data itself is the recorded speech and the mouse trace over the image. They are both time synchronized, which we depict with a color gradient. But we want the textual caption. One way to get it is via an automatic speech recognition system. Imagine it outputs a log burns on the show. It is timestamped, so synchronized with the rest. Notice the color gradient, but the result often has errors. To solve this, we ask the annotators to listen to their recording a posteriori and transcribe their answer. This gets us the correct transcription. A dog runs on the snow, but it has no timestamp. Note it's all in black. To get a correct and timestamped caption, we perform sequence-to-sequence alignment between these two results. These three synchronized streams, voice, mouse trace, and correct transcription, is what forms our localized narratives, and is what you saw in the previous video. These are the advantages of our proposed annotations. The localization is dense. Every word has a trace segment grounding it to the image. The descriptions are rich. Annotators talk about the objects, their relations, and their attributes. They are natural to annotate. This has very nice implications. We don't need to train the annotators, so we can easily scale up. And the worst case scenario is safe. There might be incomplete or not interesting annotations, but they are rarely wrong. And they are fast to produce, 2 minutes 25 seconds per image. All this allowed us to annotate at scale. We produced localized narratives for 848,000 images, covering a big part of OpenImages and the whole COCO, Flickr 30K, and AD 20K. We made them all publicly available on our website. Localized narratives captions are at least 3 times longer than most previous datasets, such as Flickr 30K, COCO captions, or Visual Genome. Stanford Visual Paragraphs is the only exception, but localized narratives provides 40 times more images. More importantly, localized narratives are the first to provide grounding for every word of the caption. On top of that, the grounding is in the form of a mouse trace, compared to a bounding box or the whole image as in all previous approaches. Localized narratives are accurate. To measure spatial accuracy, we get all occurrences of the 80 COCO classes in our captions and find the closest box to the trace. This is the histogram of the trace location normalized to the closest box, which shows that most of the trace points land in a correct bounding box. To measure semantic accuracy, we manually revise 1,500 nouns and verbs and check whether they correctly describe the content of the image. We find that semantic accuracy is 98%. So which tasks can benefit from localized narratives? Here we represent the 3 streams of annotations plus the image pixels. Standard image captioning takes an image as input and outputs a caption. Localized narratives could be more training data in this case. But we could also use the mouse traces. If we use them at train time only, they could be seen as a supervision signal for the attention mechanism. If we have them at test time too, we can perform controlled image captioning. In our work, we demonstrate this application. First, we took a state-of-the-art image captioning model and trained it on our data, and this is the result. Notice that the car is not mentioned in the caption. Next, we modified and retrained this model such that it can use a mouse trace to control the caption at test time. In practice, this could be a person with imperfect vision hovering their finger over the image to have them described out loud. The color gradient represents time, so in this case, the trace starts from the sidewalk and ends on the car. Notice that now the car is mentioned in the caption, and even these trees, since the user hovers the mouse over them. In a different case, the user starts on the car and goes in the other direction. The output caption adapts to this input trace. Changing the direction of the arrow, text-to-image generation would output an image given its textual description. But now, imagine the user starts from a blank canvas and describes the objects in the image as well as their location. The algorithm can then generate an image where the objects are at the desired spot. This is the second application that we demonstrate in our work. Imagine the user says they'd like an image with a boat in this location, for instance. From this trace, we generate an approximate semantic segmentation, and from it, we generate an image using a state-of-the-art image synthesis method. And this is the result we get. Not super exciting yet, but stay with me. Then the user says they would want water around the boat. Things get better already. Notice that the boat is closed for now. But then a person is drawn and the boat opens up. We can also add an umbrella. And if we add a mountain, the color of the water changes, so the technique goes beyond copy-pasting parts of training images. Beyond these 2 applications that we demonstrate, this table shows possible combinations of our data as input and output, and a list of works or new areas of research that could benefit from it. One of these new areas is speech transcription. With our data, one could perform grounded speech transcription, which would allow to disambiguate spoken words such as plants versus planets, given their visual representation. Wrapping up, we presented localized narratives, image descriptions with dense localization. The descriptions are rich and they are intuitive to generate, which allows us to scale the data collection up. We demonstrate 2 applications of the data and show that it can be useful for many more. Please check our website to visualize and download the annotations. Thank you.